My name is Ike Nassi, and I'm the founder and CTO of TidalScale. In the past, I've worked at several large companies like Digital Equipment Corporation, Apple, Cisco, and SAP, as well as several startups in the areas of multiprocessor systems, wireless networks, and smartphones. Today, I'll be talking about in-memory computing, specifically in-memory databases. The 3 points I want to cover today are: why does it matter? How does it work? And why hasn't this been solved before? So let's go back a little bit and talk about some industry history. We all know that the amount of data under management is dramatically increasing. This has been going on for a while and is expected to continue and in fact increase. I won't dwell any more on this. You've all heard of big data and you know what the trends are. Data is collected, analyzed, and stored in different ways, but one tried and true way is through the use of relational databases, which is a technology that's been very well studied and has been around for 25 years. It's based on solid mathematical principles and is formally described by something called a relational algebra. Don't worry, I won't go into relational algebra in this talk. Hardware and software technology have also evolved over decades. As a result of these advances, we have evolved implementations of our database technology, but we have not needed to evolve the underlying mathematical principles on which they're based. This is very good as it allows a high degree of application stability. Typically, we access relational databases through a programming language called SQL, or structured query language, which is not based on any single implementation of an RDB, but is based on the underlying mathematical and logical structure of the relational algebra. SQL has tremendous inertia in the marketplace. It's very well understood, and it doesn't have to change very much. It isn't going away anytime soon. Database programs written in SQL will generally work with all the leading commercial database products like SAP HANA, Oracle, Sybase, MySQL, Postgres, MariaDB, and others. SQL is used in many mission-critical enterprise software applications and systems and will continue to be used that way. When I was at Digital, we developed a family of computers we called VAX, which stands for Virtual Address Extension. VAX was a computer architecture that used a technique called virtual memory that gave each program the illusion of having 4 billion bytes of memory. Many programs could be run simultaneously on each VAX computer. Main memory at the time was expensive, and it still is. The key challenge then and now is to efficiently manage huge amounts of virtual memory when the amount of physical memory is much smaller. A key lesson I and my colleagues working on this at the time was that there is nothing that helped performance of virtual memory systems like having real physical memory. The more physical memory you have, the better overall performance you can achieve. Now, hardware vendors know this very well. They've tried very hard to increase the amount of real physical memory, which, as I said, is expensive, using a variety of techniques like increasing the density of DRAM technologies, increasing the number and size of caches, improving the processor and memory interconnect technology, advanced chip packaging technology, supplementing dynamic memory with less expensive and slower static memory, and using fast backing stores to shadow main memory. But these alternatives can often be expensive, hard to work with, or very slow. DRAM is much faster than many of the alternatives. Now, before I started TidalScale, I had been the chief scientist at SAP. We had started to develop a fast relational database that is in the market today and is known in the industry as SAP HANA. The database system was based on an assumption that we could always keep the database in main memory, and when or if customers needed more memory, they could just buy bigger machines with more memory. If one could keep the entire database in fast DRAM, applications would run very fast. This is certainly true, and the underlying database would not have to shuffle data back and forth to and from static memory or slower mass storage. Now, to be honest, I was always suspicious of this idea since it seemed to me to be counter to the economics of the industry. DRAM was expensive, and there were physical limits to how much memory you could actually put on a server. When I returned from 2009-2010 sabbatical at MIT, I attended a project review of our in-memory development efforts. At the end of the meeting, I looked around the room and said, now, you all know there's nothing that helps virtual memory performance like real memory, right? And you realize that our customers' databases can be quite a bit larger and can fit into the physical memory of today's servers, right? And are you sure they can actually buy a large enough server if they need to? People really in the room didn't know how to respond. It seemed like an intractable problem. About a year and a half later, I retired from SAP. I became an adjunct professor of computer science and engineering, but I could not shake this problem from my mind. I thought the ability to have large amounts of fast memory available to databases was a very important problem, and it wasn't being dealt with in the industry, and it certainly wasn't going away. Data needs were growing, but hardware capabilities were not growing at the same rate. The ratio of memory to processors was not keeping up. Yes, faster processors were becoming available, but they were not helping with this problem, and in fact, were making it worse by putting more bandwidth pressure on the processor memory interconnects. The solution that might work would be one that didn't increase the memory capacity of the physical computer, but could replace the hypothetical, increasingly expensive large physical computer with a set of replicated but much less expensive smaller ones that could be aggregated to look to a database, just like a large single one. This would result in lower system costs, more redundancy, and better performance. So I started TidalScale to deal with this issue of providing a machine that could handle in-memory databases in a cost-effective and highly performant way. Simply stated, TidalScale provides a user with a distributed virtual machine. The underlying components are inexpensive commodity servers that are being produced in high volume and connected together with an industry standard Ethernet. TidalScale software aggregates these servers to form a single virtual machine. It does this without having to change anything in the chosen operating system or the relational database. Customers can choose from among a number of standard Linux distributions like Red Hat, CentOS, SUSE, and others, and run any software supported by those operating systems, including relational systems like SAP HANA and Oracle. And like other virtualization approaches, this can be done without any hardware or software modifications. Since the underlying physical commodity servers have processors that cannot see all the memory in the collection, when a processor on one node issues a reference to some remote memory, TidalScale software needs to make it look like that remote memory is local. To be clear, TidalScale software cannot predict the future. It has no way of actually knowing in advance which virtual pages will be needed by which processors at any given instant in time. If we had perfect knowledge of the OS, the database, the applications, and the data, then all the memory could be made to appear to be local to all the processors that need them at the right time, and a database could run very, very fast. Instead, we use several new implementation techniques to achieve good performance. First, we treat memory differently depending on how it's used. Remote memory that needs to be fetched by a local processor can be easily copied. After the copy, processors on different machines read the memory with no overhead because it's local. Remote memory that a processor needs to update is more complicated. When a processor needs to update memory, we have to make sure every processor sees the same update before the processor actually reads it. To do that, we erase all the other copies, write to only one copy, and then allow that copy to be copied when and if needed. But there's another technique, and this is unique to TidalScale. TidalScale software allows for virtualized processors that can migrate to where the memory is those processors frequently need. And we can do this in groups. We can group together virtualized processors with groups of memory pages and co-locate them on the same physical server based on the behavior that we observe. This is dynamic, adaptive, learned behavior that is controlled by our unique machine learning algorithms. There is no human intervention required, and it happens at machine speed. It is done below the operating system and above the bare metal hardware. If our algorithms were all-knowing, we could do a perfect job of this and performance would be guaranteed to be optimal. Since the algorithms cannot predict the future, they can never do a perfect job, but they can get pretty close. The really interesting thing about this is that this layer of system optimizations can be good enough so that performance relative to bare metal is sometimes better with TidalScale software than without. You may find this counterintuitive, but it's true. Instead of the normal virtualization overhead you might think you'd encounter, you might think of this as negative overhead. Further, it's not just about processors and memory, two of the key resources in the system. We can also virtualize networks and storage using similar techniques. And finally, we implemented a simple-to-use system management scheme to manage this virtualized system. It is one that allows a customer to configure and boot up a complex system like this in about 30 minutes. Now, why is this happening now? Why didn't it happen, years ago? You might wonder why such a system was invented earlier. There are many reasons, but the simplest answer is that modern microprocessors, that is, those developed in the last 15 years, can now support virtualized systems in ways they could not in the past. The modern microprocessor architectures not only have support for virtual memory as implemented by modern operating systems, but they also have support for modern virtualization systems that sit beneath those operating systems. The need for this was not apparent until virtualized systems started to increase in popularity. What TidalScale did was to use some of these features in new, innovative ways that perhaps even the processor architects did not envision. After all, people did not think you could create such a distributed virtual machine capability until TidalScale created it. One other point worth mentioning is that advances in machine learning and artificial intelligence sensitized us to what could be accomplished in a dynamically adaptive environment. Today, customers regularly procure, install, and configure a system to match the needs of their applications. If they cannot procure such a system, applications may need to be modified to meet the limitations of available hardware. And if they can procure those new systems, they may or may not be sufficient to meet future needs. So instead of buying a system to meet the needs of a particular application, we have introduced a capability for a customer to create a virtual system, perhaps even by reusing existing systems, whose capabilities match those needed by the application. That newly created virtual system could have enough memory, enough processors, enough storage, and enough network bandwidth to meet the new requirements of the application. Further, those systems can be easily reconfigured in less than an hour as needs change. So, bottom line, instead of adjusting the application to meet the capabilities of the hardware, we can now adjust the hardware to meet the needs of the applications.